Hello viewers, welcome to this next lecture on NPTEL MOOC course on mathematical portfolio theory. Recall that in the previous lecture we started talking about using the financial toolbox of MATLAB in order to look at portfolio optimization problem. And in this lecture we will continue our discussion on that, and we will look at today's topic on two-fund theorem being used in order to derive the optimized portfolios. So, for this we will look at the derivation of an efficient frontier and the tangent portfolio, and with the point of tangency will later be identified as the point where the Sharpe ratio is maximum, and we will look at these problems not just in terms of the basic mean variance optimization setup, but also by incorporating some practical realistic constraints that we see in actual market. So, we start off with portfolio optimization examples. So, we will look at a few examples which mainly uses this portfolio object, that is a critical part of the financial toolbox. And the specific examples that we will look at is how to set up a mean variance portfolio optimization problem with an emphasis on a few things, namely the two-fund theorem, and also will incorporate the notion of transaction cost and turnover constraint into the problem. And we will look at the problem of maximization of the Sharpe ratio, which was an indicator of effectiveness in the management of the portfolio, and we will briefly mention two popular hedge fund strategies, namely the dollar neutral and 130-30 portfolios. So, we will just mention those since they were not a part of our regular discussion in the preceding lectures. So, first thing we do is we will have to set up the data, and we will see that how this example works for the monthly total returns. So, we are just looking at the monthly returns, and by total returns that we mean that we are talking about the returns without bringing into picture things like transaction cost and turnover constraints, and we will focus on composition of 30 blue chip stocks. So, blue chip stocks are the ones of companies which have a reputation for quality, reliability, and most importantly the profitability both in good and in stressed market conditions. And this term blue chip comes from the game of poker, where you have chips with the blue chips having a high value. So, for this purpose the MATLAB toolbox here uses data which are real data, but this data have been chosen for illustrative purposes and is not intended to actually talk about or giving investment advice. So, instead of this data which is included in MATLAB, which is called the blue chip stock moments.mat, we essentially which comprises of this blue chip stocks. So, you can use your own files for the asset parameters. So, accordingly we first load this the blue chip stock moments. So, this will give the moments of this blue chip stocks, and remember that these are just the monthly total returns. And once you have loaded this, then we'll take the we'll define M ret, that is the market return, to be equal to the market mean, and market risk is will be taken to be the square root of the market variance. So, accordingly similarly we will take what is known as the cash mean and identify is at C ret, and we will talk about the square root of cash var, which will be taken as CRSK. So, let me just elaborate what this cash mean, this concept of cash mean and cash var, and market mean and market var. So, here the cash term indicates the cash component and is used as a proxy for cash. So, you can view this as some sort of a risk free investment, and the market mean or the market variance, you can view this as that these are akin to equities or a portfolio of equities, particularly the market portfolio. Now, accordingly for that purpose we essentially look at the average return from the market mean, and we will look at the average mean of the cash, and for the counterpart risk we look at the square root of the variances for the market as well as the cash. So, the next thing that we do is we create a portfolio object, and the purpose of this creation of a portfolio object is to bring into the picture the asset list. So, we will incorporate the asset list, and we will bring in the risk free rate, which is taken to be the cash mean, and the moments of the asset return. So, we will basically incorporate the individual asset means as well as the asset covariance. So, this is just like a starting point where you set up the basic essential components that are required for the portfolio object. So, then what you do is for the purpose of comparison, what you do is that we set up an equal weight portfolio, and by equal weight portfolio I essentially mean that the weights assigned to the portfolio are taken to be all identical to each other, and we make it the initial portfolio. So, accordingly you see that we set the initial portfolio to be 1 over p the number of assets, and so that means the E risk and E return. So, that means the E here stands for the equal-weighted portfolio. This will be essentially, these values will be returned by the estimation of the portfolio moments of the initial portfolio that was set up with the equal number of weights or the equal level of weights being assigned to all the assets that are a part of the portfolio. So, the next thing we do is we will now look at how to plot this. Now, in order to plot this, we what we are going to do is that we are going to look at 3 components. So, the first 2 are the market and the cash components, and for that we recall that the market risk and market return and the cash risk and cash return. And so, for the equal-weighted portfolio, we take the risk and the return for the equal-weighted portfolio, and for these 3 components, namely the market, cash and the equal weights, we essentially then have this plot for all of this in the mu sigma diagram. So, this is nothing but on the y axis we have the mean of returns, and on the x axis we have the standard deviation of returns. So, let me just identify particular terms here. So, in this case what we are doing here is that we are doing a scatter plot. So, the first thing that we are doing is the market portfolio. So, this is where the market portfolio lies. Then you have the cash portfolio which lies here. So, as you can see that the risk is effectively 0 because it is a cash position, and the portfolio with all equal weights lies here. And then in addition to that, we also do the scatter plot, which will plot the individual mean and variances for each of the individual assets that are a part of the database with these blue chip stocks. So, for example, here you will see there are several databases. So, for example, if you observe here HPQ, that is for Hewlett Packard, and then you have GM, that is for General Motors. For example, there is J&J, so that is Johnson and Johnson. So, each of those corresponds to a whole bunch of these companies. And so, this is just a mu sigma scatter plot of all the companies that have been considered in the database, their expected return and risk as given by the standard deviation, along with the risk and return of the cash, the market and the equal weighted portfolio. So, this is the basic plot that we have for this database of blue chip stock. Now, we need to set up the optimization problem one by one and then solve for those. So, what you do is that we set up a mean variance portfolio optimization problem, and it is set up, default constraints are set up for that. So, by default constraints, it means that of course, you will have the sum of the weights being equal to 1, and in addition to that you are not allowed any short selling. That means, your weights must all be greater than or equal to 0. So, with this initial problem, the goal is to figure out what is going to be the efficient frontier. So, accordingly, we will set the default constraints as I mentioned, that all long positions with the sum of weights being equal to 1, and then what you do is that we estimate the efficient frontier, and then we get the estimate the portfolio moments of the efficient frontier and store them as the P risk and P RSK and P return. So, in this case, what does the efficient frontier look like? The efficient frontier looks like, it is pretty much the same diagram that you have here with the that you got earlier, the scatter plot, but on top of that. So, in this case you observe that it is the scatter plot of the market, cash and the equal-weighted portfolio as well as the individual assets, but on top of this we have this blue curve which is going to be the efficient frontier of this database of individual assets of all the blue chip stock companies. So, now we will talk about the tangent line to the efficient frontier. Remember that we will eventually make use of the goal. The first problem that we will look at is going to be the two fund theorem. So, the two fund theorem will basically make use of a combination of investment in cash as well as a risky portfolio. So, now what you do here is the following, that the portfolio that has been already been set up, the object that was set up earlier, it already has the risk free rate. So, what you do is the following. So, we can generate the tangent line, and what is the tangent line? So, the tangent line is nothing but it is basically a collation or a collection of all those points on the mu sigma diagram. As you vary your risk free rate from 0% to 100%, or that is from 0 to 1. So, accordingly, we set the budget of this risk free asset from 0 to 1, and then what you do is that we essentially what we now have is we will have the scatter plot. As before, we will have the efficient frontier, and then now we will essentially generate this line. So, here you observe that we will make use of the alphabet P risk and P return for for the portfolio itself, and then when we talk about in order to generate the efficient frontier, and the Q here will indicate the tangent line which is tangent to the efficient frontier. So, now what we do is that in this case, so now what you have to do is, now that we have set up this mu sigma diagram for each of the individual assets along with these three assets, and we now have the efficient frontier as well as the tangent portfolio. So, we now need to, what you do is that we want to obtain efficient portfolios with a pre-specified value of either risk or return. So, what you do is basically that means that you want to figure out an efficient portfolio for your either, where you either pre-specify what is the level of risk that you are willing to take, or you pre-specify what is the return that you are expecting, and it is necessary to obtain the range of returns and risks amongst all the portfolios. So, accordingly what you do is, in order to accomplish this, we talk about what is known as the estimate frontier limits function. So, what is this estimate frontier limit? So, estimate frontier limits, basically what it does is that before you can actually set your target for your return, or you want to set a maximum tolerance for risk level, you first really need to know that what are the values of return and risk at this endpoint and at this particular endpoint, so that you do not end up choosing a return that is not even anywhere on the efficient frontier. So, accordingly you get this. So, if you observe carefully, so here we say that the monthly portfolio returns are between 0.9% and 1.8%. So, this graph is, remember that this is based, this efficient frontier is based on the monthly returns of the individual assets. So, accordingly you observe that for the returns, that means from the return at the bottommost end of the efficient frontier to the topmost end, it ranges from 0.9 to 1.8%. Similarly, if you observe carefully, and from 3.5 to 9%. So, this so in annualized terms, this means that it will range from 11.2% to 21.5%. So, let me just be more specific, that if you look carefully here, that this value that you have here, this is somewhere around 0.11, and the top value is somewhere 0.21. So, that means the range is from 11.2% to 21.5%, and this is what translates to 0.9% and 1.8% on a monthly basis, and likewise you have 12.1% to 31.3%. So, if you observe carefully, the variance that you have here is probably 0.12, and this is around 0.31. So, that means the annual risk percentage is from 12.1% to 31.3%, and this manifests to an equivalent monthly value, and in order to move to the monthly value, you just cannot divide by 12, but you have to factor in a square root of capital T, which is the square root of 12. Okay, so now that we have this entire setup of the assets along with the efficient frontier and the tangent portfolio, we now can talk about once this has given us an idea as to what range of returns that you are looking at and what is the risk range that is available to us. So, now you are in a position to answer our prior question of determining a portfolio with a targeted return and a targeted risk. So, by targeted we mean here that there is a specific target that we have in mind as far as our return is concerned, and there is a level of risk that we are not willing to exceed as far as our investment strategy is concerned. So, accordingly we say that, so what we do is that, for example, for illustrative purposes we will input a target return of 0.2 or 20%, and this means that we want a expected return of 20% and we will target the risk at 0.15. So, that means we are willing to accept up to 15% of the risk. So, accordingly what we do is that we will estimate the efficient frontier by return, and we will essentially take the target return by 12. So, this is what is going to be, this is the, we will input the annualized target return and risk, and then we will convert this to the monthly return and risk, and so this gives us the estimated. So, in this case ARSK and ART, these are going to basically give us the target return on a monthly basis. So, that means that it is going to give us a portfolio or the efficient portfolio with the targeted return of 20% per annum, and in the second case you see that we are taking the target risk and dividing by square root of 12. So, remember that I said that we have to divide this by square root of capital T. So, in this case we get the efficient frontier for the second case when our target risk has been set at 15%. So, once we do this, what we do is that we now keep extending our plot that was done earlier. So, remember that, so as before we have all the return and risk of the individual components along with whatever we had seen earlier in terms of the market, equity and cash return, and we have the efficient frontier that we see here. So, then what we have here, we observe that in addition to whatever we had seen earlier, we now have identified the two specific portfolios. Now, this is a portfolio which has the portfolio on the efficient frontier with mu p or the expected return to be 20%, and this the other point here, this is going to be the 15% level of risk for the portfolio. And it is that portfolio which lies on the efficient frontier with a 15% risk. So, now we need to actually look at determining the exact portfolio for the 20% return and the 15% risk, and so accordingly we will use a blotter so that or a table that will consist of the portfolio weights. So, first of all we will use a blotter which essentially takes 100% into AWGT. Remember AWGT, this is going to be the one corresponding to the targeted return, and so it turns out that the portfolio with a 20% target return will comprise of these 6 individual assets. Observe here that amongst these the highest weight adding up to about 80% of the portfolio are for UTX, which is 56%, and WMT is 31.253. So, this UTX is Raytheon Technologies and WMT is Walmart. Okay, now, this was what was identified as a blotter corresponding to a weight for the targeted return of 20%, and the next thing we do is that we will consider the BWDGT, which is for the targeted risk of 15%, and we will store the portfolio in terms of percentage as this blotter, which you call as B blotter. So, this as you can see has a much larger number of assets that are in it. In particular, I want to identify the ones which actually have more than 10%. So, the first one you can identify is Triple M, which is 16%. So, this is the company 3M. The next is you have MO and this MO, which is 15%, this is Microsoft, and then we have UTX, which is 10%. So, as already mentioned, this is going to be Raytheon Technologies, and you have 25% for WMT, that is Walmart, and 12.69% that is ExoM, which is Exxon Mobil. So, you have been able to actually now identify the portfolios that you want as per your requirement. Now, you are now free to actually set whatever target return you want and whatever target risk you want, of course, within the range that was obtained in the previous step. So, once you pick up any return or risk within the range that has been obtained, you can essentially immediately through this command you can estimate the weights of the specific portfolio as per your personal preferences. So, this is, you can see, is a very useful tool, because it straight away gives you the weights of the portfolio to satisfies your constraints. Now, so far what we have been doing here is that we have been essentially looking at only the cases that of a mean variance portfolio optimization by looking at these assets without even actually accounting for the practical reality of transaction costs and turnover. So, now we look at an extension of the problem to make it more realistic, and accordingly we incorporate the transaction cost. So, again, you know, the portfolio object that is there in the MATLAB financial toolbox, it is amenable and has the provision for accounting for the transaction cost as a part of the individualized problem. So, accordingly what you can do is that we can set up individual costs for each asset. So, I mean that this is the transaction cost, for example, you might have to give a brokerage, and you can so as an illustrative purpose, we set up a uniform transaction cost across all assets, and once you do that, we can calculate the efficient frontiers of gross versus net. So, the gross efficient frontier is nothing but the efficient frontier without this costs being included, and the net portfolio is the portfolio where these costs are actually being included. So, here for the illustrative purpose, we say the buying and selling costs are both 0.0020 or 0.2%, but of course, you know, you are free to choose other values depending on what exactly is the cost involved, and instead of having uniform cost, there is of course the room for setting up individual cost for each individual asset separately. So, this, you know, the set cost is now assigned to this variable q, and now we are going to make an estimation of the efficient frontier after having incorporated the costs in terms of this q, and then we get the estimation of the portfolio moments using this q and the q weight. That means, q weight is the weights of the efficient frontier after having incorporated the cost in as q. So, again we now look at the plot. So, here we have the efficient frontier without the transaction cost. So, observe carefully here. Here everything is pretty much the same as before. You have all these individual assets, market and cash, and this equal portfolio. And as I said that, you know, here you earlier we had looked at what is the gross efficient frontier, which is this case, which is the dotted line, and this bold line that you have here, this is the net efficient frontier. So, this is one constraint that had to be included. The second constraint that we consider for inclusion is what is known as the turnover constraint. So, you would recall that from the previous lecture, we talked about that that the portfolio object, in addition to transaction cost, it also can accommodate turnover constraints. And remember that the turnover constraint was basically some sort of a restriction on the extent to which you can do your trading, because you have to reshuffle your portfolio from time to time in order to obtain the best optimized portfolio. But in order to ensure that there is not too much of volume of transaction, because that also incurs cost. So, accordingly we will demonstrate in this example, the next example that you are considering here, that a turnover constraint, it produces the efficient frontier in the neighborhood of the initial portfolio. So, accordingly what we do is that we now you know, in addition to the cost of 0.0020 of buying and selling, that is 0.2% that is applicable in case of the cost, we set the turnover at 0.2 or 20%. So, accordingly we set q. So, now this q that we have here, this of course, as before the buying and the selling cost are included. So, this is what you have done when you consider only the transaction cost, and on top of it now we add to Q as turnover as per our specification, which in this case is 0.2 or 20%. So, accordingly what you do is that we will now have the efficient frontier that is being estimated and the output being set to give you the weights and the quantity of buying and selling. So, once you have this, of course, again you will have a similar kind of efficient frontier. So, here if you observe carefully that here we had this unconstrained efficient frontier, and here in this bold line we have the efficient frontier, which has accommodated for a maximum of 20% turnover. Okay, so now let us now talk about tracking error constraint. So, let us now talk about, again we go back to the portfolio object that is inbuilt into MATLAB, and we can handle tracking error constraints, where tracking error is the relative risk of a portfolio compared to the tracking portfolio. So, here we do is that we have a portfolio that is being actively managed, and in order to track the errors we introduce a tracking portfolio, and the goal is to ensure that you have to find those efficient portfolios with tracking constraints, with tracking errors that are within 5% of the tracking portfolio. So, essentially it is some sort of controlling portfolio, and the efficient portfolios is that you want is the one that is not too far from this tracking portfolio. And in this case the specific example that is being considered here is that these errors are within the 5% limit of the tracking portfolio. So, now how do you set up the tracking portfolio? So, here is a tracking portfolio in this example, and there are different ways in which you can do this. So, in this case the tracking portfolio is being collected as a sub collection of 9 assets from an equally weighted portfolio. So, accordingly we will identify the index of the assets that you want to include in the tracking portfolio. So, out of say 30 assets, you have identified that you will include those particular assets which are indexed 15, 16, 20, 21 all the way to 30. These are the ones that you are going to include in the tracking portfolio. So, that means that while the main portfolio has a larger number of assets for inclusion, the tracking portfolio will have a subset of those collections of those assets, and the tracking error is then set to 0.05 or 5% divided by square root of 12 for the monthly tracking, and the tracking portfolio here is set to be zeros 31. So, that means what you do here is the following, that the tracking portfolio here initially is set to be have weights all 0. And what you do is that then you assign the weight of 1 to those points in those components of the tracking portfolio which are there for inclusion. So, this will mean that for the 30 entries in the portfolio, in the tracking portfolio, only 9 have non-zero values which are all set to be equal to 1, and obviously then the sum of those weights is going to be equal to 9. So, then you divide then by the sum of this tracking portfolio, which is 9. So, that means that all the 9 entries of 1 that are there will now be converted to 1 by 9. So, again we estimate the efficient frontier, and this is the efficient frontier of Q, which incorporates the tracking error and takes care of the tracking portfolio. So, here we will estimate the portfolio moments and for the weights, and then the one with the tracking portfolio. So, what you do now is that we will calculate the efficient frontier in both the scenarios. So, in the first one, what we will do is that the one with the dotted line, this is going to be nothing but the unconstrained efficient frontier as before, with no constraints being imposed, and this red one is the tracking portfolio. So, this is the expected, this point here represents the expected return and risk of the tracking portfolio, which comprises of those 9 assets that have been identified with an equal amount of weight being assigned to each of them. And then on the basis of that, what you can do is that without tracking, this dotted line would be the efficient frontier, but with tracking, which only allows an error of 5%, the efficient frontier obviously gets reduced significantly, because it can't be too far from the tracking portfolio. So, it gets significantly curtailed, as is evident from the length of the efficient frontier, and it is that part it is essentially that part of the efficient frontier is closest to it, which essentially satisfies the condition that the tracking error should not be more than 5%. Okay, now we will look at an example of the combined turnover and the tracking error constraints. So, suppose that we set the turnover to a maximum of 30%, and we say that the tracking error can be 5%. So, now we are looking at the constraint problem, which brings into picture the constraint of the tracking error that was there in the preceding example, and along with it the combined turnover. So, accordingly, here we set the turnover to be 0.3, and we set the initial portfolio, the portfolio to be this, and then we have this tracking portfolio as given here. So, the initial portfolio is set to be the portfolio to be an equal weighted portfolio. So, there are three aspects here that needs to be taken care of. The first is that the turnover is set at 30%. Now, in order to start your generation of the efficient frontier portfolio, you need to have some initial portfolio. So, the initial portfolio is set to be an equal weighted portfolio, and the tracking error portfolio is the same as that has been set before. So, there are two portfolios here, one is the initial portfolio and one is the tracking error portfolio. So, accordingly, what you do is that so here Q is set to be you set the turnover, and you have this initial portfolio that you have here, and you estimate the portfolio moments for Q, and you calculate what is going to be determine what is going to be the efficient frontier. So, if you observe carefully here, this is a cash and the market. So, the reason why we are only identifying cash and market, because these are the two important portfolios. And then we have this unconstrained efficient frontier that we have in the top, and this is the initial portfolio, and this is the tracking portfolio. So, starting off with this initial portfolio, you are able to reach the tracking portfolio, that is tracking efficient frontier, which is determined by a constraint of being the tracking error being no more than 5%. So, you start from here, and with this initial constraint and with this tracking portfolio, those portfolios which satisfy the condition of 5% tracking error, that will constitute this significantly truncated efficient frontier that is given here in bold. Okay, so now the next thing that we want to look at is what is known as the maximization of the Sharpe ratio. So, remember that the Sharpe ratio is a critical measure of portfolio performance analysis, and it is given by the return to risk. So, it is the excess return to risk, and particularly we are interested in a portfolio that maximizes the Sharpe ratio, and it turns out that this is the tangency portfolio that we had discussed in the class. So, in this case we know that the reason why you want to maximize the Sharpe ratio is because the Sharpe ratio does is that it looks at the excess return over risk, and the larger this value is, the larger it indicates that you are able to achieve a larger amount of excess return per unit value of the risk that is given by the standard deviation. So, the maximum Sharpe ratio portfolio is lies on the efficient frontier. So, accordingly what you do is that we set the, so in this case we plot the efficient frontier with the goal of maximizing the Sharpe ratio. So, in this case we use the estimate max Sharpe ratio command to get the corresponding weights, which results in the maximized Sharpe ratio, and then we we determine what is the corresponding risk and return by making use of the command of estimate portfolio moments. So, if you look carefully here, in this particular case, again we look at the mean of returns and you look at the standard deviation. So, and you see that here we have the scatter plot along with everything else that was there earlier. Of course, here I have not put in any constraint. So, this is my efficient frontier, and the only thing over and above the basic efficient frontier setup that we had done at the beginning of the class is the identification of this particular point on the efficient frontier, which maximizes the Sharpe ratio, and this is the tangent portfolio. So, interestingly, it turns out again if you do a blotter of this. So, the blotter of this is going to be again we look at the blotter here is going to be the weights of all the portfolios that maximizes the Sharpe ratio. So, this will give you our weights in terms of percentage of the individual assets that constitute the portfolio with the maximum Sharpe ratio. And here if you observe carefully, while most of the weights are extremely low, some of the important words that you again have, you observe it is going to be those similar kind of names that are showing up here. So, 15% here for 3M, 13% here for Microsoft, 22% here for Walmart, and 18% here for Exxon Mobil. So, here you can actually do a cross check and verification that the maximum Sharpe ratio is indeed maximum by this. So, we now come to the illustration that the Sharpe ratio is the tangent portfolio. So, if in order to obtain that, we again just look at the previous problem, and remember that in order to prove that the Sharpe ratio is indeed the tangent portfolio, what you have to do is that we have to then generate the tangent line, and only when we generate the tangent line, that the point where it touches the efficient frontier is going to be the tangent portfolio. And if it turns out that the point from a visual point of view, if it turns out that the point where the tangent line touches the efficient frontier is the same as the portfolio with the maximum Sharpe ratio, then the illustration of this problem actually is accomplished. So, accordingly we just look at this particular previous figure that we had here, and to it we will now add the tangent line. So, in order to do that, again we set the budget where the risk free investment can be from 0 all the way to 100%. So, we have estimated the efficient frontier for this. So, remember that again we have the scatter plots of the individual assets, MRSK, CRSK, ERSK correspond to the market, cash and equal weights portfolio. And this SRK and S return, this is going to generate this particular point, which is the point portfolio with the maximum Sharpe ratio. And of course, here the PRSK and QRSK. So, PRSK it will generate the efficient frontier curve here, and QRSK will generate the tangent line. So, you observe very carefully that here this tangent line it touches the efficient frontier at this point, and as you can see visually this is going to be the same as the point which is the maximum Sharpe ratio. Okay, so, let us now just come to the last topic. So, I will just explain this in a narrative fashion because this is something that we actually have not done in the lecture, but nevertheless it gives you an interesting insight into more sophisticated approaches of financial investment, and these are what is known as a dollar neutral hedge fund structure, and the second one is what we call as the 130-30 fund structure. So, here these commands that will be done here, it basically makes use of the portfolio optimization tools in hedge fund management. So, hedge funds essentially are funds with a large amount of assets, and typically assets under its management, and typically they will be handling assets on behalf of high net worth individuals or people who have a lot of disposable cash for investment. Now, two popular strategies that are adopted for portfolio optimization by the hedge fund management, these are what are known as dollar neutral and what are known as 130-30 portfolios. Now, let us now first talk about what is the dollar neutral strategy. So, the dollar neutral strategy, as the name suggests, involves some sort of neutrality. So, more specifically, this means that the dollar neutral strategy is the one where one invests equally in long and short position such that the net portfolio position is 0. So, that means that you get into a long position in a certain number of assets and you get into a short position in certain other assets, and the total valuation of the long position is equal to the total valuation of the your short position. So, that means that it is something like you are adding and subtracting the same number, giving you the net valuation of your portfolio to be equal to 0. So, you can actually go through this example on how to set up the dollar neutral portfolio. So, if you observe carefully here that here the exposure is set to be exposure and minus exposure. So, this is the one that corresponds to the long position and this is the one that is said to be the short position, and here also you end up getting an efficient frontier of the dollar neutral. So, if you observe carefully here that this is the efficient frontier that we have here, and this is the line, this is the tangent line, and this point of tangency is the one with the maximum Sharpe ratio. And here so accordingly this bold curve here, this is what is the dollar neutral efficient frontier, and this dotted one is the standard or the usual efficient frontier. And if you observe carefully, so here you have set forth the setup for the dollar neutral portfolio, and you have estimated the efficient frontiers. And so, accordingly this to efficient, from this to efficient frontier, you see that your dollar neutral portfolio that you have, that particular efficient frontier is at a higher level than what is given by standard efficient frontier. So, this means that obviously that you have been consistently getting a better return as compared to the standard efficient frontier, but of course, you have to recognize that to obtain this obviously involves a higher level of risk. So, accordingly, because mainly because you have indulged in a short position, and that is the reason why typically these are strategies that are used by hedge funds on behalf of individuals who actually are in a position and fiscally and financially well off enough for in order to take such risks. So, accordingly you actually see here that we have a dollar neutral portfolio with the respective weights. Now, as I said that your total position must be equal to 0. So, you observe here that the weights are specified here. So, for example, if you look carefully here J and J, that is Johnson and Johnson, since this is positive value. So, that means you have this is the position, your long position, and 0 is your short position. On the other hand, if you look at JPM, that is JP Morgan here, then it is minus 2.5271. So, that means his long position is 0 and his short position is 2.5271. And then you confirm the dollar neutral portfolios, and you observe that the long position is the same as the short position with a negative sign, and consequently the net is going to be equal to 0. Okay, so let us now come to the second example of hedge fund strategies, and this is what is known as the 100-30-30 fund scheme. So, as the name itself, again just like dollar neutral, the name itself in this case of 130-30 fund structure suggests that it is going to involve some sort of a proportion of 130 and 30, and since 130 is a larger number and 130 minus 30 is equal to 100. So, you can immediately guess that it is a structure where you have a net long position, but you can involve in short positions. So, in this case your long position is 130 and your short position is 30. So, what you do here is accordingly in this case what you do is that you your sum of the weights is equal to 1, and then you have a leverage of the 0.3 weightage, and accordingly. So, that means that it is something like you already have a portfolio in the usual way, and then you short 30% of that amount and you generate the funds. So, essentially you have 130% of a long position, and then you have a 30% of a short position. So, the difference between them which gives you 100% of the short position. So, here this is an example where you can see that, that this is the dotted one is the standard efficient frontier, and the one above it in the bold, this is going to be an efficient frontier involving this 130-30 portfolio strategy. And here is the Sharpe ratio for that, or rather the Sharpe ratio, the point or the portfolio with the maximum Sharpe ratio. And even though the name suggests that it is 130-30, but it is not a very rigid structure that you have to involve 130% and 30%. All that you need is that the sum of these two should end up being equal to 100%. So, it could be it could start from a 120-20 structure, that means 120% long and 20% short, and go all the way to 150-50 structures of 150% long and 50% short. So, if you observe carefully that in this particular efficient frontier, so you can see that the one, so that means the particular weights that for the 130-30 portfolio that have been enlisted here, that is nothing but the portfolio corresponding to the maximum Sharpe ratio on the efficient frontier of the 130-30 portfolio. So, again here you see that there are certain weights which are negative, for which the position is a short position, and then there are certain assets like say PG, which is Procter and Gamble, for which the weight is 17%, and so that means your long position is 17% and the short position is 0. And again you see here, you see that if you confirm this these positions, so you can confirm this position, and it turns out that this position, the long position is going to be 130, you just add this up, and the short position is 30, and consequently the net position is 100. So, this takes care of these several examples in case of portfolio optimization problems. So, so let us just do a recap of what we have done in today's class. So, our class today was mainly motivated by the two fund theorem. So, we started off by looking at a database of some blue chip stock companies, and then we look at their moments, and we looked at the efficient frontier of those along with the scatter plot of each of the individual assets which constitute that particular database, namely there are 30 assets that are there. And then we looked at what is the efficient frontier, and we brought about a tangent line to that efficient frontier. Now, once you have done that, once you determine what is the efficient frontier, we brought about into constraints such as the constraint, the first constraint that we looked at was trying to figure out the points on the efficient frontier or that portfolio for a specified level of expected return on the part of the investor, and this was followed by the optimal portfolio on the efficient frontier for a pre-specified tolerance level of risk of the investor. Now, next we looked at the efficient frontiers with the targeted portfolios, and we looked at the efficient frontiers by incorporating two constraints, namely one which involves the buying and selling, or that is the transaction cost, and the other was the turnover constraint. In addition to that, we looked at the portfolio optimization, and we used the maximization of the Sharpe ratio as the goal, and it turned out that we could visualize that the maximized Sharpe ratio portfolio is the one which is the point of tangency of the tangent line and the efficient frontier. And then we looked at a couple of interesting applications from the more sophisticated setup of hedge fund management, namely the dollar neutral portfolio valuation, where you actually have that the long and short positions in the portfolio are exactly matching each other, so that the net value is 0, and the other setup which is called 130 setup, where 130% of the assets are invested in the long position and the 30% are invested in the short position, or equivalently some 100 plus x percent of the portfolio is in long position and x percent is the short position, resulting in a net portfolio position of 100%. So, this brings us to the end of this lecture, and in the next lecture, which will be the concluding lecture of the course, we will talk about a few more examples, again making use of the financial toolbox of MATLAB. Thank you.